Support for WPR comes from Rutabaga Paddle Sports, committed to offering outdoor clothing and camping gear to get people outside, on or off the water. Test paddling at 2620 Rimrock Road. RutabagaShop.com.
I'm Lee Rayburn in for Larry Mealer today on The Larry Mealer Show, and I believe X-rays were sort of an accident when they were first invented. I know that the X in X-rays stood for the unknown, as I don't think they were entirely certain how this technology worked when they first stumbled across it. X-rays, generally speaking, use radiation to penetrate through bodies and create images of internal structures. We think of it most commonly as our teeth and bones. We go to the doctor's office or we go to the dentist to find out what's broken on the inside or needs fixing. But X-rays and X-ray lasers have come a long way since their first invention, and our understanding continues to evolve in this technology. Here to help us understand it better is somebody who's on the cutting edge of X-ray technology. Uwe Bergman is a professor of ultrafast X-ray science in UW-Madison's Department of Physics and a researcher at Lawrence Berkeley National Laboratory in California. Uwe also worked as a staff scientist at the U.S. Department of Energy's SLAC National Accelerator Laboratory in Stanford, California. Do you have questions for our expert about X-rays and how they are being used to so much as see an electron move? And once we understand that, what does that mean about our greater understanding of our universe? From the tiniest little objects of our reality to the big picture of the world we're living in. You can join our conversation by calling 1-800-642-1234. That's 800-642-1234. Or sending us an email anytime to talk@wpr.org. Uwe, thank you for joining us today.
Thank you very much for having me.
Yeah, and let's start with how you see X-rays. You've been working with this technology for a while now, and I'm curious how you see X-rays as a tool that's used to help us increase our understanding of the world. How so?
Well, X-rays are really amazing in the following sense. They have a few properties which are very powerful. One of them is the one which we all know, which means that they can penetrate matter and we can get images, for example, the images of our body or the images of our teeth, or even the images like when you go to the screening at an airport. And to do that, we use very extremely high energy X-rays. By high energy, I mean they have a very short wavelength. That means they can penetrate very well. It doesn't mean that they are necessarily very intense. Intensities means how many we have or how focused they are. High energy means that they are very penetrating. So for all those practical applications, which most people are familiar with, including the popular culture X-ray vision of Superman, those are done with really very, very penetrating X-rays. When you talk to researchers who do science with X-rays and use the most advanced X-ray machines in the world, we mostly use X-rays they're not as much penetrating. They're still penetrating, but they have other properties which really are very, very powerful. And that two properties. One of them is they have very, very short. They still have very short wavelengths. Mm-hmm. Why is that important? The reason why you cannot see, for example, a cell, right, the inside of a bacterium or a cell with visible light, the only reason for that is the wavelength is too long. It misses those small features. The wavelength of light is about, let's say, 500 nanometer, which is a half a micron, right? And the size of those objects are just smaller, so you cannot see them. X-rays have wavelengths typically of order some angstrom, and an angstrom is a tenth of a nanometer, so it's already much shorter, and then so it's basically 5,000 times shorter than visible light, and that means with X-rays we can bring to light atoms and molecules, and that's one of the two properties which makes them very, very powerful.
That they have very short wavelengths, and you can see at the very atomic level using these short wavelengths.
Exactly. So I would say the most famous example was the discovery of the DNA by Rosalind Franklin's image, and Watson and Crick. Obviously, they got the Nobel Prize, which was in the 1950s, right? That's already 75 years ago, 70 years ago. And they basically used the technique called X-ray diffraction or X-ray protein crystallography, so they make copies of molecules, and then they scatter X-rays from them. And by reconstructing those measured images, they can then reconstruct the molecular structure of those proteins. And they can do that basically with a very high resolution. So that means we can really see where each of the atoms is sitting in a big biological molecule. And that's how they basically discovered the double helix structure of the DNA. I like that example because it really opened, it really showed the immense power of X-rays, right?
Uwe, how are some of the ways that you have used X-rays in the past? What are some of the things that you've looked at and researched prior to your most recent work?
Yes. So I have, thank you for that question. So I could give you a long answer, but let me just focus on a few. So I have used since I started my research in the late 1980s and then 1990s. We have used powerful X-ray machines called synchrotrons. These are large, round accelerators, and they produce very intense and focused streams of X-rays. And we have also used them in the similar way as I just described in terms of diffraction. But I'm mostly an expert on a technique called X-ray spectroscopy. So spectroscopy comes from the word spectrum, which is like the spectrum of a rainbow, for example. These are the different colors of the rainbow, and we use the different colors. We use X-ray colors, so you cannot see them with your eyes, but you can make them visible in a detector. And we use these spectra to understand not just the structure of proteins, but we even look a little bit further inside. So, for example, in the case of if you talk about a big protein structure, you are interested in the overall composition, but then if you're interested in even more details, you can zoom in on a specific element, let's say an iron or a manganese metal, which is inside one of those proteins, and you can then test the surroundings, the intimate surroundings of that atom with even more precision, and you do that by spectroscopy. We have also, go ahead.
Well, I was just going to take a step back and go through that a little slower for myself because it's your focus. It's X-ray spectroscopy, and it is using these very short wavelengths to look at the atomic levels. But what you are seeing as results ends up being a spectrograph of different, I wouldn't say colors because they're not necessarily viewable by the naked eye, but wavelengths that would come up as visual wavelengths. Is that correct?
Well, the wavelengths, they are, yes, it's correct that they're wavelengths. They're not visual. We visualize them.
Okay.
Right? So they're not visual in the sense that our eye can only see wavelengths of, let's say, 400 to 700 nanometer, right? These wavelengths are angstrom, but we can bring them to light because we can record them, and then we can visualize them, and we can actually plot them in a graph, or we can plot them with different colors. We have all kinds of ways how to bring them to light. But what is important is that what is contained in these so-called spectra, right, which is a really kind of an abstract word. I appreciate that. But what is contained in these spectra, when you do the interpretation, you can actually see how the atoms and molecules, how they are individually arranged and how they are talking to each other, and that makes this technique called X-ray spectroscopy very, very powerful. It's a very powerful technique.
So you can see not just at the atomic level, you can see interactions at the atomic level. But you've been using two of the fastest X-ray lasers on Earth to come up with your latest science. And the published paper that you have recently published seems to suggest you have stumbled across something that is getting international attention now. Tell us a little bit about what it is you are researching and why your most recent discovery is getting so much attention, Uwe.
Oh, thank you for that question. So, yes. So when I let me just go back to.
Yeah.
So we as scientists we have used these synchrotron sources, right? These which are also very large accelerators, and in fact, in Wisconsin has in Stoughton had one of the first synchrotrons in the world, and was operating it until 2014. It was a very successful program. And there's another very large one at Argonne National Lab outside of Chicago. It's the largest synchrotron in the United States. So these are powerful X-ray sources, and they are used internationally. There are many of those around the world. And in 2010 or 2009, a new form of X-ray sources came to light, and these are called X-ray free electron lasers. I'll drop the word free electron just to keep it short. So we call them X-ray lasers. And these X-ray lasers are even more powerful than synchrotrons in the following sense. They make pulses which are, first of all, more intense, much more intense, up to like 1 billion times more intense. And they make pulses which are very, very short. So these X-ray lasers who started basically in 2010 or 2009, and they have been around now for about 15 years or so, and there are only 6 machines around the world which make such X-ray laser pulses. They are now about 1,000 times shorter than these pulses from the synchrotrons, and they are on the time scale of typically like 10 femtosecond. So now, if you ask, oh, what's a femtosecond?
Yes.
A femtosecond is a millionth of a billionth of a second. So which is
it's an instant.
So it's short. It's very short. So it's like basically 15 zeros and then comes the 1. That is a femtosecond. And why are femtoseconds interesting? They're interesting. And by the way, I'm not yet at our research. So our research comes next, right? So I'm just telling you what these new X-ray lasers have been able to accomplish, and they really have caused a revolution in X-ray science. Right?
This is the setup here, because we started with the synchrotron X-rays and how they could accelerate in a way that allowed us to go even further, even smaller, even faster. But then in an almost an exponential way, these X-ray lasers that you're now using, Uwe, seem to be even smaller, even faster, down to what the rest of us would consider a mere instant. You're able to capture what's happening at a atomic and even potentially subatomic level.
Exactly. And as I said, I'm still setting it up because I'm not yet at our work. So let me talk a little bit about these X-ray free electron lasers first.
Uwe, I'm gonna hold on, Uwe. I'm gonna stop you there because I have a caller here who wants to chime in, and I want to get to that before we get to the breakthrough research that you are, in the process of uncovering and just recently published. Let's go to Guy in Neilsville first. Guy, good morning.
Yeah, good morning. I work in a medical field, and I attended a webinar about 2 weeks ago. And on that webinar, we were talking about a virus and how it infects cells and how it binds to a receptor. And that receptor also is an amino acid transporter. It's kind of interesting. But they were talking about how tightly this virus binds to that receptor. And they showed an image of the receptor site with the virus binding. And they said it's so detailed, it was like a photograph. It was 12 hydrogen bonds. And, having gone through chemistry back in the 1980s, I heard you talk about the DNA, but to actually be using this to look at interactions, biological interactions at the atomic level is just totally amazing. I wondered if you could comment on that image, that sort of image.
Uwe?
Yeah, thank you for that question, or for this comment, actually. This is exactly, those images are, at the moment, they are most likely have been produced by X-rays, by the synchrotron X-rays. And there's another technique which has now gained a lot of power in the last few years. It's called electron microscopy. And electron microscopy also, these electrons in the microscopy also have very short wavelengths, similar to the X-ray wavelength. So that technique has been coming up. But the largely dominant technique over the last 50 years to uncover exactly the kind of information our caller just said is from synchrotron radiation facilities. And there have been I think up close to 200,000 protein structures have now been solved with that X-ray technique, with the same, generally speaking, the same X-ray technique that Rosalind Franklin and Watson and Crick used in the 50s, just with much more powerful X-ray sources. So with much, and the tools have evolved, and they are extremely powerful methods for doing that. So thank you. That's a very good example.
Yeah, I appreciate the call, Guy. And Uwe Bergman is our guest, professor in UW-Madison's Department of Physics, researcher at Lawrence Berkeley National Laboratory, and published a recent study that in part was done here where I am at the UW-Madison campus into what could be some of the fastest, most intense X-rays to capture the shortest pulses of an instant that we have seen to date, and what that means for our understanding at the subatomic scale, at the fastest points of what we know to be speed as it stands. What do we find when we're on the precipice of this new technology? That's next. I'm Lee Rayburn in for Larry Mealer today, and you're listening to WPR News. I'm Lee Rayburn in for Larry Mealer today, and coming up afternoon, the weather guys are back. Steve Ackerman and John Martin join us to help explain our air quality, our heat indices, and what the heck's happening with this Wisconsin summer. They'll be answering your questions as well today afternoon here on the Larry Mealer Show. But right now, we're talking to one of the scientists who apparently has generated the shortest pulse of high-energy X-rays that we have seen to date, using two powerful lasers to stimulate inner shell electrons. And these inner shell electrons closest to the atomic nucleus at the fastest rates of speed we've ever seen, in a way that could allow us to see for the very first time electrons dancing. Uwe Bergman, our guest, professor of ultrafast X-ray science in UW-Madison's Department of Physics, where he teaches, and he also is a researcher at the Lawrence Berkeley National Laboratory. And I apologize for the big build-up, Uwe, but I wanted to understand it better before we got into it. Your research, your published paper, and what we are finding with the strongest pulses at the fastest speeds we have ever used these X-ray lasers with before.
Yes, thank you. I really appreciate it, and I also want to thank the question of which we got. So, if I can go back to the X-ray free electron lasers, because those are needed to do the research which we did, and I mentioned before the break that with these X-ray free electron lasers, we can make pulses which are a few femtoseconds long, and so this is a few millionths of a billionth of a second. And that time scale is important because that is the time scale of chemistry happening. And what these X-ray lasers have allowed is when you have, let's say, a chemical bond forming. So you have a reaction, a chemical reaction, for example, CO oxidation. So you want, in a catalyst of a car, for example, you want to remove the carbon monoxide and turn it into carbon dioxide in a catalyst. The real process happens at a very fast time scale. And every real process, all the processes in our human body happen if you want to go really into the atomic picture of a chemical reaction, it happens very, very fast time scales. And with these free electron lasers, X-ray free electron lasers, we have now been able to access that time scale, how a bond is formed and broken, how let's say, a spin, which is another property of matter, is flipped from one side to the other. but it is still not the time scale which I'm talking about in our latest work, because that's another 100 times faster than that.
Wait, so you talked before, Uwe, about how we weren't able to originally see a human cell because we didn't yet have X-rays at a short enough wavelength. But now we can actually see the elements changing in front of us with speeds, with the current speeds and wavelengths of our X-rays. But you're saying now that you've gone 1,000 times faster than that, even?
Well, yeah, I would say 100 times.
100 times.
I don't want to exaggerate, right? We are, it's about 100 times, but we are in a new time regime. Yes. So with the X-ray lasers, we have now been able, for example, if you go back also to the question from the caller. So if you and we have and my collaboration, I'm part of collaborations which have actually done such work. We can now look at these, let's say, these proteins, these large molecules, and we can see how they change. For example, we are interested in studying photosynthesis. How does sunlight split water to produce oxygen, the oxygen we breathe? And we have now made movies where we show that with exactly that X-ray technique on the atomic level.
You have showed, wait a minute. You have showed visual representations of the literal chemical reaction that is photosynthesis.
We have been able to do that over the last 10 years, yes. But that is not, this latest discovery goes one step further, okay? So do you want me to talk a little bit about the latest stuff?
Oh, yes,
right?
please. I mean, because in my mind, Uwe, I'm thinking, well, then what's further than that? I feel like we figured it all out. We can rest on our laurels now. We've seen how photosynthesis works. We're seeing how electrons can move between atomic particles. What more do we need to see, and what did you find?
Okay, so, well, first of all, we are scratching the surface. Let me be clear about that. I mean, life is so incredibly complicated. I mean, it is so complicated that it's mind-boggling. And we are just using some of the not even most complicated reactions which we understand, but we have a path. So that, I think, is really important. We have the tools now to really look into the world on that level and on that time scale. So in our latest work, we had this idea, or if you want to call it, or we wanted to see whether we can use these super powerful pulses, which come from an X-ray free electron laser, which is a large, kilometer-long, big accelerator. And we said, can we make our own little atomic laser pumped with this large laser? And this work has been shown about 10 years ago or so that it's in principle possible. And we have started to do some research with that. So we put in, let's say, a manganese foil or a copper foil, and we hit it with this very powerful, intense pulses. What happens next is that the foil itself generates its own inner shell atomic laser pulse, and we were using those pulses to study like the properties of the materials, and we were just interested to see what comes out. What we found, and it was really a little bit accidentally, that we drive it very, very hard. So if we crank up the intensity to the absolute maximum, and let me tell you how high that is. We have, at the moment when this X-ray free electron laser hits the sample, we have the same intensity as if we would focus all the sunlight which hits the Earth to 1 square millimeter. It's an insane amount. It's an insane amount of power density. Like it's 10 to the 20 watts per centimeter square. It's like an incredible power. But what happens at that instant? We generate a strong lasing event inside the sample, and when we looked at what comes out, we were surprised because the pulses didn't look like what we expected. They were much broader. By broad, I mean they had more X-ray colors in them. Right? Normally, we would have expected, let's say, to have a certain range of X-ray colors, But what we found, they had like 5 times, 10 times as much X-ray colors. And we said, where do these X-ray colors come from? They are not in the sample. There is no transition. There is no atomic transition in the sample which can generate these colors. And what we found out from finally understanding it with using simulations, which were developed by my colleagues in Hamburg, some of our collaborators, and then implemented by one of my postdocs, Tom Linker, who is actually also the first author of the paper, these broad colors indicated that our pulses were even shorter, even 100 times shorter than the ones we pumped it with. And that goes back to Heisenberg almost. There is a relationship. The shorter a pulse is, and by the way, in optics that is well known as well, the shorter a pulse is, the broader, the more colors it has. You cannot have a very short pulse which only has one color. If you make a pulse extremely short, it gets broader and broader in colors. It has more and more colors. And what we have discovered, that some of our pulses were 60 to 100 attoseconds, and that attosecond is 1,000 times shorter than a femtosecond. So they were the shortest pulses with hard X-rays ever produced. The world record, you can look it up on you can just type it in, and AI tells you it's 43 attoseconds, but that's not for X-rays, that's for ultraviolet light, right? Okay. Or extreme ultraviolet light. We are much shorter in wavelength, so we are about almost 100 times shorter so in wavelength. And so these are now the shortest pulses which have ever been made. Yeah.
So you're using the shortest pulses, the fastest X-rays, but you found results that you weren't expecting and had to bring in what sounds like an international team of scientists to help you understand what you'd actually done with what appears to have been, a focused energy beam that is on par with the sun itself. But you did not expect these samples. And what it reminds me of, Uwe, is it reminds me a little bit of the way X-rays were invented in the first place, that you got results that were surprising to you, weren't entirely sure where they were coming from, but may have led you to a whole new frontier of understanding X-ray lasers and lasing.
The discovery of X-rays by Röntgen, like that was a earth-shattering event. I don't think we are on par with that, but but we are happy to be able to. Actually, it took us really 5 years, and the teams on these X-ray laser experiments, right? Those are large teams to start with, and we had collaborated the person who has developed the theory, the group, Nina Noring and I. We had collaborated already for quite some years. The theory was not in place, so they had to develop actually a 3-dimensional theory, because the effects we saw could not be simply explained like by just simulating the forward direction. We had to add the all 3 dimensions of the propagation of the light in the sample to come to this result. So that took some time, and yes, you're right. We were surprised, but I should point out this same phenomenon which we saw was also, and this is kind of makes it a historical circle, it was also discovered already 70 years ago before the laser. So before the laser was discovered, Towns and Ortler, the Towns is the father of the laser, right? They discovered with microwaves, they discovered a phenomenon called Rabi cycling, and that is the phenomenon which we now have observed with X-rays. So no one ever thought at the time that you will ever see such a thing with X-rays, right? They were happy that they were able to see it with light, and so that has led to the development of lasers, right? And lasers are now everywhere; they're extremely important. But we have now pushed this to actually X-ray vision. So we now have these very, very powerful short, extremely short pulses with X-rays. Yeah.
Uwe Bergman, our guest, professor in UW-Madison's Department of Physics and researcher at the Lawrence Berkeley National Laboratory, talking about his work with the fastest, strongest lasers we have ever seen and how they have led to a whole new frontier of X-ray laser technology and what the implications could be going forward. I want to invite you to our conversations with questions you may have about Uwe's work. 1-800-642-1234. That's 800-642-1234. Or you can email us, talk@wpr.org. That's talk@wpr.org. So you use these X-ray lasers to shoot like magnesium or copper, and you shoot it with what is basically a focused laser beam of the sun itself with its intensity, and you do it at such a small amount. But when you do it, as I understand it, Uwe, and I'm trying to think it through here, the pulses that you are shooting at the copper or magnesium or whatever your element is, well, there are pulses that emanate inside these elements that are even shorter than the ones that you pumped them with, and the output is what you visualize as a result as more colors than you would have expected in the first place, which led you to try to come up with a whole bigger understanding of what's happening at our smallest levels of reality. Is that about right?
Absolutely, you got it 100% right.
Yes.
And in fact, it's not magnesium, it's manganese, but I mean,
okay,
it sounds
thank
very
you.
So manganese and the another important thing is, because our pulses are so powerful, I mean, each time you shoot the foil, you basically make drill a hole in it and make a big crater, right? So the thing basically explodes, and so you have to move the sample quickly to the new spot. So we basically, when we do these experiments, we basically perforate our sample. So we look afterwards, we look on a microscope, we have like a perfectly perforated sample afterwards, because each single shot smashes out all the atoms, and they get sprayed all over the hut. And our collaborators in Japan and at SLAC, where we do this experiment at Stanford, they're sometimes not happy about us like polluting. So we need to make like a little chamber to capture all this debris which we are causing when we hit the sample. And yes, so in the sample, a second pulse is generated, and that is the attosecond pulse. Yeah. Exactly correct.
So, but what is creating that second pulse that seems to be, I don't know, generating some energy from your original X-ray laser?
So the way how it works, in a sense, it's a little bit like so we come in. Let's say our original X-ray laser comes in with one color, right, and it has to have enough energy to remove those inner shell electrons, and then our secondary laser, our attosecond laser, shoots out slightly redder color. So for example, in the analogy of visible light, and again, I should stress, X-rays don't have colors, not for the eye. We just use the word. We come in with let's say with a bluish color with femtoseconds, and we hit the copper or the manganese, and we come out with a more reddish color with attoseconds. And we have a spectrometer where we can actually separate them out very easily. So we can see we are only interested to see the little bit more reddish X-ray pulses, right? And because those are these extremely short X-ray pulses.
What are the ramifications of this breakthrough in using X-ray lasers? What has piqued your curiosity about what you may find now with this technology, Uwe?
Well, thank you. I think this is a really, of course, a very important question. I think we can move the field forward in two, in my opinion, important directions. And I should point out, a lot of work is also going on with these attoseconds. I mean, it's a whole field now. In fact, the Nobel Prize in Physics 2 years ago was awarded for the discovery of attosecond pulses, and you can check it out. So in the optical regime, right, and in the also ultraviolet regime, attosecond pulses have become a thing, right? It's a whole new field of science which is taking on. It hasn't been possible with X-rays, and it hasn't been possible with shortwave X-rays, the ones we have. And that's what is exciting. So we can now enter this field of attosecond science. So what is happening at that level? First, I mentioned like a bond, a chemical bond is formed and broken. That's femtosecond. So that's 1,000 times slower or 100 times slower. Attosecond is basically what is a bond. When I draw a molecule, I just draw like electrons and I draw like atoms but that's not how reality is.
Right.
Because electrons are not circling in orbits like some people say, oh, the electrons is like the Earth circling the sun. No, it's not. It's completely different. It's quantum mechanics, right? It's a cloud. It's a delocalized cloud. And with this attoseconds, we can look inside that cloud now. We have a way to see actually to see what we mean by when we say it's a cloud. And I think that aspect is very exciting.
So we have gone from seeing the chemical bonds at our smallest atomic level to now with this attosecond high-energy X-ray lasers to seeing what these bonds actually are. Not just the cloud of electrons that surround a nucleus, but the instant that stops them in their tracks so that you can see the direction, the path that the electrons are taking, Uwe?
Exactly. So, for example, let me give a simple example. If you take a benzene ring, which is made out of 6 carbons, right? And if you would ask a chemist what is that, well, he said, oh, these are all delocalized electrons. Mm-hmm. So you can, at any given time, you look at them, they are all over the map, right? And with these attoseconds, you can say no, actually they are not. We can actually tell you where they are at even shorter times, because we have always assumed that at this short time scale it all averages out. But now with these attoseconds, you can start to finally look inside of that, and that gives us new understanding about what is actually a chemical bond. And one really famous example is water, right? Water has a hydrogen bond, and we do not understand it because water is such a mysterious liquid. It has so many unusual properties, yet everyone uses it every day. We drink it. I'm drinking it right now. And the reason why we haven't really fully understood it yet is because we don't understand how the bond, how the hydrogen bond is not really fully understood. And I believe once we have this attosecond science, we can answer such questions, which are really absolutely fundamental to our understanding of nature and our understanding of life and chemical reactions.
Uwe, if we can understand those bonds, then in ways we can start to think about how we might manipulate them to, say, desalinate water and provide fresh water for the entire globe. I mean, the ramifications are infinite and probably not even well considered yet, because what you're talking about would have seemed absolutely impossible just decades ago. So now we're changing the entire way we think about the smallest and shortest levels of our reality and how they comprise what we're living through today. It's fascinating, and I want to get to the callers here at 1-800-642-1234, where Alicia and Racine is standing by. Alicia, good morning.
Hi. I just caught the end of this, and my mind is kind of reeling right now, but I mean, this is something that I'm wondering if it could create a whole new theory, like, blow string theory and quantum mechanics out of the water, and even more simple things like laser surgery or whatever. I mean,
right?
Like, where do you want to go with this? Like, are you trying to create a whole new theory of reality with this?
Well, there have been some big questions about the quantum theories of our physics, so let's ask Uwe Bergman what this could mean for the actual theoretical aspects of our reality.
Yeah, thank you. It's a really good question. So we do string theory. I mean, first of all, string theory is a complicated topic because it's very difficult to test, but this is not the realm. So in order to get to those questions, you need to have much, much higher energies. You need to go to like a CERN particle accelerator and look on the inside, let's say, on the inside of a proton, of a quark or in a proton, etc. So we are not in the field of high energy physics, right? We are in the field of chemistry but quantum but quantum mechanics, right?
Yep.
And I think the point that you mentioned, quantum mechanics, is a good one, because one of the really interesting things I'm very excited about with this process which we are using and have discovered, we now can also consider making entangled light with X-rays, and that means we can do so-called what is called quantum optics and quantum information. So there is a really good chance that, and that is being currently pursued with a lot of my colleagues actually at Wisconsin and other universities are pursuing that. You might have heard of it. It's a new field called quantum computing, right? And they are using, so it's all done with visible light and all kind of different approaches. And there is potentially a way to use X-rays to look into such quantum entanglement. And I think that is a very exciting direction which this research could potentially go in the future.
Alicia, I'm so glad you asked. Thank you for calling. Uwe Bergman is our guest. Recent published study with some support and help from scientists around the world have found that we may begin to understand not just the chemical bonds that create our reality, but how those bonds operate, how they move in what we would consider to be an instant. But our physicists are not getting down to even shorter periods of time with even stronger X-rays and what this may mean for our understanding and ability to improve our reality. Uwe Bergman's professor at UW-Madison's Department of Physics, researcher at Lawrence Berkeley National Laboratory, and he continues to answer your questions next here on The Larry Miller Show. I'm Lee Rayburn, and this is WPR News. Tomorrow on The Larry Miller Show, we take a look at the new book, Piracy on the Great Lakes, True Tales of Freshwater Pirates. Also, take a tour of the planned city of Greendale and talk to the editor of Lake Superior magazine, all coming up tomorrow on The Larry Miller Show. I'm Lee Rayburn, in for Larry today. And our guest this hour, Uwe Bergman, professor in UW-Madison's Department of Physics and researcher at Lawrence Berkeley National Laboratory, who's getting international notice right now for a recent paper he published, which takes a look at some of the strongest lasers on Earth being used in the fastest instance that we've ever used them before, and finding out at the very molecular level, not just the chemical bonds themselves, but how the bonds are created and destroyed in what you and I would consider an instant. I want to invite you to the conversations. Your questions have been great so far. 1-800-642-1234. That's 800-642-1234. Or email talk@wpr.org. Let's go to Carolyn LaCrosse next. Carolyn, good morning.
Good morning. I had a question. I was wondering if this discovery could deconstruct the chemical bonds in PFAS, and could we use this to take all that PFAS pollution out of our water?
Carolyn, thank you so much, because Uwe, I believe you've done some work with lasers and X-rays and artificial photosynthesis before. You mentioned that we do not understand water because of our lack of information about what these chemical bonds actually are doing. So tell us, would PFAS cleanup be something that we could see as a possible application of this technology?
Can you say, I'm not sure I understand what is PFAS? Is that
the forever plastics that have seeped into our water supply, and what we're going to do about that in the future.
Okay, yeah. Well, the techniques we are using are not, you wouldn't use, I don't think you would use any of those tools to do the cleanup. Mm-hmm. But understanding, let's say, if one were to come with a let's say a chemical way of purifying water from microplastics, right? And by the way, a lot of research is done in how one can purify things and remove things and add things. The understanding of how such a process would work on the molecular level, right? That could be interesting for maybe not our other second laser pulses, but in general for X-ray lasers, and there could potentially be some light shed onto how such reactions happen. So,
sure.
So I would say, yeah, not so much for for these attosecond pulses, but generally speaking, any of those technologies, that's why I gave the example, for example, the example on the CO, carbon monoxide oxidation, right, which you have in a catalytic converter, right? There's a lot of questions as what limits the effectiveness. What limits the effectiveness of any catalytic reaction which we are doing, right? And having these X-ray laser pulses, X-ray free electron laser pulses, can be used to understand such mechanisms. And once you understand the mechanism, you can then modify the way how you do the work, the chemistry work.
Great question, Carolyn, and thank you for asking it, because it may be something that would be worked up in the future and we could understand it better through this science. Professor Bergman, Steve emailed to ask you to comment on what sort of instruments you use to measure the timing of the events described in the attosecond realm, which, I keep thinking of as what would be an instant to me. How do you measure that instant?
Yeah, so we in our work, we have not measured it directly in the time domain. We have inferred to it from this broadening which I had mentioned. So there are now so-called streaking cameras, very complicated streaking cameras, and they have been used for softer X-ray work. For the ultraviolet work and for some of the softer work, they have been able to develop some instruments. We are thinking of maybe in the future developing an instrument where we can measure it directly in time. For our work, that has not been done. What we did is we showed that the only way the pulses can be as broad, no other way the pulse can be as broad other than being very, very short. So we did do an indirect measurement of that time.
I had a caller who didn't stay with us but wanted to know if another application of your research could be possibly treating neurodegenerative diseases.
Well, treating is one way.
Okay.
Understanding is another way.
Yes.
So I would always say, and by the way, synchrotron X-rays, even the structure of the coronavirus, right, the COVID-19, has been done. They use the synchrotron to solve that structure, and a lot of research in medication and how to treat diseases comes from understanding how the affected molecular structure looks like, right? And so I would say we are not in the business of treating. We are in the business of seeing and understanding how these things look like. And then with that information, one can go into a pharmaceutical company or a doctor could then devise a method of treatment, right? So we are not, we are one level removed from the application. We are more in the question of showing it how it looks like and understanding it, and then another team of researchers can do the work of developing a drug, for example, or a treatment.
I was curious, Professor Bergman, you had mentioned that Stoughton had one of the first synchrotron X-ray accelerators in the world until 2014. I'm wondering what happened to the synchrotron in Stoughton and whether or not you have the technology here in Wisconsin to move forward with your work.
Oh yeah, so it's a really good question. Stoughton it was at long wavelengths X-rays, so it was more like extreme ultraviolet and soft X-rays. But it had two rings, and there was an upgrade. And like every of those research projects, I mean, it has a certain lifetime. And in 2014, I think there were other facilities around the world and around the country with more competitive properties, and that was the end of the lifetime. But Wisconsin has been pioneering, right? And they have a very strong history, and even a lot of Wisconsin scientists use these other facilities around the world and have made leading contributions to these other facilities. So there are now a lot of smaller tabletop instruments. They are not as powerful, but they are real. So we have, for example, in my lab, I have one in Wisconsin. which can do femtosecond pulses, right? And it doesn't do them with hard X-rays. It doesn't do them with extreme ultraviolet light, right? And they're not as powerful, but they are also extremely powerful in studying material science and chemical reactions. Right?
Uwe, I want to apologize because we are out of time for this hour, but I want to thank you for a fascinating discussion and sharing your research with us and our audience today. Thank you so much.
Thank you. I appreciate it.
Uwe Bergman, professor at the UW-Madison Department of Physics and researcher at Lawrence Berkeley National Laboratory. Coming up next hour, the weather guys are back. Steve Ackerman and John Martin join us to answer your weather questions. What have you been seeing in the Wisconsin skies? I'm Lee Rayburn in for Larry Mealer today, and you're listening to WPR News. Wildfires, rainstorms, extreme heat we're seeing in southern Wisconsin today. It's been another summer across the state, and climate scientists tell us to expect more of the same. But how many of us understand the causes and results of some of the climate change we've seen? I'm Lee Rayburn in for Larry today on The Larry Mealer Show. And joining us for the next hour, our weather guys. John Martin is a professor and former chair of atmospheric and oceanic sciences at UW-Madison. And Steve Ackerman is the former vice chancellor for research and graduate education at UW-Madison, also an emeritus professor in the Department of Atmospheric and Oceanic Sciences. And we want to invite you to the conversation. Questions about Wisconsin weather, trends, phenomenon. What questions do you have for them? Give us a call, 1-800-642-1234. Send us an email, talk@wpr.org. That's 800-642-1234 or talk@wpr.org. And John and Steve, welcome back to the Larry Mealer Show.
It's great to be back here. Yeah.
Let's start with the heat today. Our heat indices could reach 104 degrees across southern Wisconsin. That's expected to last until at least 8 tonight. But what am I to make of these heat advisories and what they mean for me?
It means you got to be careful if you're outside, especially and active. And if you're in a place without air conditioning, without good ventilation, you can run the risk of getting so much water retained in your body on days like this that you cannot cool yourself down by perspiration and get overheated. And is it hypothermia or the other way?
Yeah.
Is it hypothermia when you get overheated, or is it hyperthermia? I forget which one's which.
Hypo is the cold one.
Okay, so
hyperthermia. Get in the sleeping
Yeah.
bags.
Yeah, you got to be really careful on days like this.
Yeah. Drink water if you're outside.
So take those advisories seriously. They're nothing to
sneeze at.
Yeah, no, those advisories are being issued by the government, by the National Weather Service, and that they take that very, very serious with high integrity.
I know some people that take it as a challenge. All right, time to do yard work, but that's not a good idea.
That's not
Find
me.
the shade at a minimum. If you just can't put it off, find the shade.
Time to find a pool.
Yeah.
There you go.
It's critical.
It's an excuse to not do the yard work and not
That's how it works in my house, Lee. I'll tell you that right now. Why don't you go out and trim that tree? Well, then I'll lose the shade.
I've got an advisory. Exactly. Let's go to Elizabeth in La Crosse, who has a question for you guys. Elizabeth, good afternoon.
Good afternoon. Thanks for taking my call.
What's your question?
I was wondering what specific or immediate impacts we're seeing with the elimination of NOAA's Office of Oceanic and Atmospheric Research, the cuts to climate research, cooperative institutes, and staffing levels. What we're seeing in regards to these like severe weather forecasting, long-term climate monitoring, and like public safety in the U.S.
I believe it was April when the Trump administration dismissed experts who were working on the next climate assessment, pulled down the website for it, and removed the phrase climate science from government websites. I also know you guys have a recent article on the National Climate Assessment that was released a couple years ago now. So what do these cuts mean as you guys see it? And I want to ask both of you, and Steve, I'll start with you.
Yeah, I think it's really a shame. Because it is going to impact our forecasting. One of the things we rely on in forecasting, particularly as we get into the fall and the wintertime, is knowing what the upper air is doing and knowing it accurately. And because of the cuts, some of the stations, I think it was in Nebraska, are reducing the amount of weather balloons that they launch in order to make those measurements so we can identify where the jet stream is flowing.
And now it may be hard to see what that impact is, only because we don't have enough data yet. It takes data, collection of data, to really see what the impacts are going to be in the long run.
Or a loss of that data.
Or a loss of that data, right. And a long series, so you can compare, what's happening in the last couple of months to what's happening prior to eliminating those radio sounds, as an example. And the same thing with the climate. It's just, it's important for us to monitor what is going on, and to pretend that climate change isn't happening is just no scientific integrity there, I don't think.
Yeah.
John, what about the question of federal funding for NOAA and weather stations and what that means for us?
Yeah, I mean, I think it's a long fuse problem. It's one of the things that this administration is pretty good at, is picking at things that will take a long time to have an impact. And by the time people actually are impacted by some of these changes, they may forget what was the origin of this impact that they're currently experiencing. And, it's going to take a long time, maybe a couple of years, before systematic reduction in the observational capability that Steve was just talking about is going to have an impact on the way that we can foretell what's coming in the weather. If I were a property owner on the east coast of Florida, let's say I owned a giant mansion that I bought for some reduced price by some way right near West Palm Beach, I would not want to have taken the Defense Meteorological Satellites out of service this summer, because they are the only thing that can look into hurricanes with any sort of ability to tell what's going on inside the storm overnight. A whole fleet of observations for overnight forecasting of hurricane intensification is now gone. And there's no reason for that. There was no motivation for that other than we can do it, we're going to do it, it's going to make a bunch of people mad who work at universities. That's why they did it. And it's going to cost people lives.
The argument is government efficiency, I believe, but you would argue that that is, in the long run, an inefficient way to operate a government.
What's your definition of efficiency? Do you want to deliver the best product at the best amount of time with the best lead time? That's how I would define efficiency. All of these changes will do absolutely the opposite in all three of those categories of that definition.
Yeah, that's a good definition of efficiency.
Yeah.
Right?
So,
doing it right.
What if we decide that we want this federal funding to return? If we want a fully funding NOAA and we want these weather stations back in action, is that something that can flip a switch, or is that something that would be an inefficient thing to restart?
I think it would be hard to reset, because you lost a number of people who are already trained.
That's the key.
And not just trained, because we do the training here at the university as well, but have the experience to know how to apply that knowledge that they'll get from the classroom.
Yeah, expert judgment takes years of practice to develop, and when you forsake it and you get rid of it willy-nilly, it takes a whole generation to reinstitute that expert knowledge, and there's not going to be any handoff of it from this current generation that's all been dismissed to the latest young people who are coming into the field with advanced knowledge of new techniques. It'd be a perfect, it's been a time-honored way of doing it. You give the advice and experience of the prior generation to a bunch of kids with new tools.
Right.
That's how you make progress.
And that sounds like it could be stopped.
It's going to be curtailed at a minimum.
In a follow-up email, Fred emailed here to ask what you guys think of the Trump's Environmental Protection Agency's plan to end greenhouse gas regulations and the role that could play in our climate. Steve?
Well, we know that that's one of the issues we're dealing with climate change, is the amount of greenhouse gases that we're putting into the atmosphere. And so to stop monitoring that, to stop caring about that, well, that's just saying we don't care about climate. We don't care about the people who live in Florida who are sitting on the coastline and need to know what's going to happen with hurricanes, or up here as well. What's going to happen if we don't have winters?
Right. This is, to me, this is an example of one of many examples of the clown show nature of the administration when it comes to these kinds of issues. It's like taking the worst behaved kid in the 6th grade class and making him or her the monitor of behavior for students in the class. You don't do that. You take the advice of experts on problems like this. You don't decide just, again, because you can, that you're going to stop paying attention to something that every expert in the world will testify to the fact that it's causing problems. And those problems will multiply in the future if we don't get a hold on them now.
And I want to ask you a little bit about that. When we flip the switch on climate change and say we're not going to post it, we're not going to talk about it, we're not going to look into it, what is the real world ramifications of that? Maybe we feel better about our climate because we're not told all the doom and gloom that it's getting worse and there are ways to make it better that we are choosing not to take. Take us down the road where this persists, and this is the world we live in, and what does this world look like in my daily life?
Yeah, and I think in a daily life, because we're talking about climate, you may not notice anything. The question is, what is it going to be like 5 years from now, 10 years from now?
Yeah.
And if we don't collect that data, we will not know what is being changed. My guess is if we're not going to be monitoring greenhouse gases, that it's going to get worse, right? Because
more greenhouse gases,
right, we're
more
going to have
global
more
warming,
in it, and that's going to warm the climate even more.
Yeah, there's no surprise about the physical result of it, but I think there's also a psychic and sociological result of these kinds of willy-nilly cuts and dismissing of really important challenges that we all face. Steve and I are of the generation, I think, that was brought up watching the Apollo program mature into something that was just fantastically exciting.
Science continued to expand who we were as a people, as a human race, and the world that we lived in continued to get bigger and greater. That science was taking us somewhere. We were going somewhere with our understanding and using the scientific method to test out our world.
Right. And in addition to those things that are tangible results of it, there's an inspirational quality to that exploration, into that reliance on learning and science and experts that you really, if you aren't careful, you dismantle that whole psychic structure. And young people growing up today, 1st through 5th through 7th and 8th grade, are going to be less than challenged because they're being told there's no problems. And so I don't think that's good for our culture.
That they don't have to worry about it because they don't see it, because we stop publishing it and stop looking into it.
It's not something you should think about.
It does not exist. Fascinating. A little more practical back here at home happening right now. Mandy in Viroqua called, couldn't stay with us. She heard a derecho warning was issued today and is wondering about the implications for Wisconsin. First of all, what's a derecho warning?
It's a derecho is a kind of storm it's reminiscent of the kind that can develop tornadoes, but these are straight line winds. And I think I heard about this. This is going to be like 100-mile-per-hour wind forecasts in parts of South Dakota and South Dakota and Minnesota later today. So in the afternoon, it appears as though in the forecast, the feature that's controlling that threat is going to dissipate rather rapidly late in the evening. And so it won't have a big impact on much of the state. I suppose the far southwestern and western parts of the state might feel something from it, but probably not in its most robust state. That's at least the current forecast.
And with regard to the warning part or the watch part, when we're looking at severe weather, NOAA, National Weather Service, if it looks like it might happen, then they'll issue a watch. They're basically saying, watch out for this. When they're issuing a warning, then that means either it's occurring and heading your way.
So watch is a heads up, and the warning is get your head down.
Do something. Get your heads down. Just a 100-mile-per-hour wind. I'm not... get indoors, I guess.
And make sure it's bolted. It'll strip paint off the side of bonds, that kind of wind. That's what it'll do.
Jim in the town of Middleton has emailed to say it seems that some weather systems coming from the southwest have a localized split that goes around areas to the northeast, such as Pine Bluff or the town of Middleton. Is there any meteorological data that would support what he calls a Blue Mounds effect, where a weather system hits something and goes two separate ways? I kind of feel this way sometimes about weather. It feels like it just missed us somehow, or is that just the way it feels?
I'm trying to think. I remember hearing about this, and it was, I don't know if it was in Blue Mounds or where it was, about the weather systems always going around that area. I've never seen the data to support that.
Okay.
But, people who live there who either want the data, whether they or don't want it, probably will draw that conclusion.
It's a plausible explanation for a repeated observation if it's repeated. And sometimes we have a tendency to kind of exaggerate the repetition. But if it is always happening, that's a plausible explanation. Although I agree with Steve, I've seen no systematic study that's come to that conclusion about the topography here in the southwest part of our state.
There's your scientific method right there.
Two
scientists going through it, trying to figure out
data. You can probably take a look at that.
You could do the work to figure it out.
At least if the systems are precipitating anyway.
John Martin, Steve Ackerman, the weather guys are with us today, and we invite you to the conversation at 1-800-642-1234. What have you seen from Wisconsin's summer weather so far, and what questions do you have about what to expect next, or some phenomenon that you'd like to know more about? Call us, 1-800-642-1234. Send us an email to talk@wpr.org. I'm Lee Rayburn in for Larry today, and you're listening to The Larry Meeler Show. I'm Lee Rayburn in for Larry today on The Larry Meeler Show. And if you have not signed up for WPR's new daily newsletter yet, do not wait. Curated by our own Jenny Peak, you'll never miss the day's top stories, must-listen audio segments and interviews, exclusive feature photos, behind-the-scenes conversations with our reporters, and you get it all in your inbox once a day. So sign up right now before you forget. WPR.org/newsletters. That's WPR.org/newsletters, and stay informed and connected through WPR. Our guest, Steve Ackerman, Emeritus Professor at UW-Madison's Department of Atmospheric and Oceanic Sciences, and John Martin here as well, the weather guys. John's a professor and former chair of Atmospheric and Oceanic Sciences at UW-Madison, and we're taking your calls and questions at 1-800-642-1234 or talk@WPR.org. We'll go to Ed in Madison next. Ed, good afternoon.
Good afternoon. I know my question is not exactly a meteorological question, but I am concerned about human survival in this climate change. Someday we may be in a real tough situation because it doesn't look too well that we're going to keep addressing this concern, especially with the Luddites that are in power. So I was just wondering what you think of carbon capture technology. Does that offer a realistic solution or at least a significant help in trying to stop this climate change?
Ed, thank you for the question, and I'm not sure our guests right now are the best to answer it, but Steve, I'll ask you what you understand about carbon capture and what it might do.
Yeah, the question that I always have, and again, I'm not an expert in it, is that once you capture that, what are you going to do with it, right? Because if you want to keep it from getting into the atmosphere as a greenhouse gas, then, having trees, for example, more trees, which is a great thing, and they suck up carbon dioxide in their photosynthesis processes. But once they die, that carbon dioxide then goes back. So I think it's important to look at, in addition to looking at how do we not put as much carbon dioxide in the atmosphere. That seems like something we could more easily control. And I think, the climate's going to get really hot and warm and unbearable in some places. But I don't think it's going to threaten the human survival because we do live in really extreme climates right now in terms of really hot deserts or really cold polar regions.
Yeah, I appreciate the perspective, Ed, but John, is carbon capture or carbon prevention our best method going forward if that were a concern?
I wish I were expert. I'm going to have to preface anything I say by reminding everybody that I'm not, but I wouldn't guess anything's really our best bet, and we got to use every tool available. And so I would guess that carbon capture, as it continues to mature, is going to be a pretty powerful weapon that we can use, but it'll only be it'll reach its greatest effect only in conjunction with other efforts. So I'm hoping for the best on that, and I think it will contribute to an alleviation of the problem, but it won't get over the fact that we're ignoring it, by and large, right now. But that ignorance is temporary. I think that it's just not going to last. It won't win the day. The question is, and the frustration is, as 3 years tick by, how much more do we have to do to get ourselves out of the hole that we dug for 3 more years that we didn't need to be digging? So.
I feel like science has reached some sort of PR catastrophe, that nobody's spoken up for science for so long, or it's been so ubiquitous in what we've come to expect in our quality of life that nobody's actually stopped to say, hey, this scientific method is very important, and if we turn our back on it, we don't know where we're going.
Yeah, I think that, Lee, is a symptom of a broader problem, which is a disrespect for expertise, no matter where it is. expertise in anything. My local mail person is better at figuring out how to get that stuff done than I could be.
You know how complicated a toilet is? I do not know how
Yes.
complicated a toilet is, and that
Exactly
could be
right.
trouble for me if I didn't have a toilet expert that I could call in.
It's precisely what I'm talking about,
Yeah.
and I know we're both in earnest, and we have completely begun to have a great erosion of respect for expertise, and it leads to some critical problems, and we got to get over it.
So how do we, I feel like I just need to advocate for science and what science has done and how science is used not to prove something, but to disprove things and find better ways. It feels like we're feeling our way through the darkness, but getting there.
Yeah.
And then when we drop the scientific method, it just feels like we're feeling around in the darkness, and somebody
I
needs
think
to
so.
speak up for that.
Yeah, I think so. I agree with that.
And I think shows like this do that.
Me too.
Trying.
Trying. I mean,
And bringing
you were
in
talking a pretty
experts.
scientific expertise prior to us.
You're right. That there is this entire world out there that experts understand and can explain and show you sort of a window into it. And if you saw that, you could see where we're going. And that is an exciting way to live.
It is.
Yeah.
It is.
But
And-
you turn that light out, and all of a sudden, you don't know where we are, where we're going. And it
Right,
feels...
and underlying that understanding is decades of hard work by each of those individual scientists. Nobody's born understanding anything, and if you become an expert in something, that's testament to the fact that you've worked hard to become an expert at something, and you ought to be part of the conversation.
Well, I appreciate that perspective. Let's go to Dave in Oconto County next. Dave, good afternoon.
Good afternoon. With the budget cuts affecting the use of our satellites in monitoring the space and the atmosphere of the Earth, and also looking at the position of the elliptical position of the North Pole, which right now we are in the decline of that elliptical position, which brings the North Pole closer to the sun, which creates a warmer global warming atmosphere, which then also is affecting the natural part of the Earth, creating the methane gases, along with human inhabitants who adds more to it. So with the budget cuts, we won't have that ability to monitor where the position of the Earth's axis really sit. Is there any discussion on that lately?
Boy, I have not. I mean, you're right. That's one of the variations with regard to natural climate change, what I call natural, in the sense is how Earth orbits the sun. And sometimes it changes so it's further away. And as you're pointing out, sometimes it's pointing at a different angle. And that is important to know what those natural changes are in order to really confirm what the human impacts are and what we're doing. That goes beyond what the natural variations will be. And yeah, I mean, I think that the cuts that they're having in the weather satellites are certainly affecting and will continue to affect our ability to do weather forecasting.
Yeah, and here's where, the timescales of some of these processes are being very different from one another. The precession of the inclination of the Earth is on hundreds of thousands of years timescale, so it's not something we have to worry about for tomorrow. So though that's never an argument for not observing things, it won't be an impactful lack of observation on that particular issue. But on many other ones, of course, it will be.
Yeah. Dave, I appreciate the call. We'll go next to Jeff, who has a house on a Madison lake. Jeff, good afternoon.
Yeah, hi. My family's had a home on Lake Mendota since like 1900 on the west side. And just observation over all the years that we've seen countless storms. They'll come in from the west, and they always go around the north side of the lake or the south side of the lake. We'd always think of, you mentioned earlier about the Blue Mound effect, but we wonder if it's not the lakes. It's very, very rare, but once in a while the storms will go around the north side of the lake and then come back from the east. And those are the worst storms that we've seen. Just so you know, we really support, the work of NOAA and the climate scientists, and yeah, we're just pretty appalled at what's all going on.
So are these thunderstorms that I live on the north end of the lake, and so so what I'm in the area where we would get a lot of rain, and I'm happy to get that rain as long as it doesn't flood. But so are they thunderstorms that you think that go through the north end and then circle around and hit the area from the east?
Yeah, well, it's like I said, we've only seen like once in a really great while. but does it, I mean, once every 10 or 20 years, kind of a thing like that. But otherwise, the storms, we always see them, like I say, you can hear them rumbling coming in from the west, but then they always go to the north side of the lake or to the south side of the lake. But we rarely have had, a big storm hit us that's, we're over by Spring Harbor and that part of the area is where our family's home is there. So,
Well, the lakes during the summertime, the water temperature is almost always cooler than the land temperature around the lake. So, like on a day like today's another example. And that will set up a small scale and probably most of the time ineffective lake breeze around the whole shore. And that is going to produce a region of low-level divergence over the lake, which is exactly the opposite kind of wind field that the storm wants to that's going to survive on. But my guess is that most of the storms are pretty well developed and have their own internal circulations that overwhelm that weak lake breeze that probably develops. So I bet it has a smaller impact than you think. However, if a storm is just beginning to develop, let's say in Middleton or in Cross Plains, maybe it doesn't have a strong enough internal circulation to overcome some bias that the lake can impose. And that might be part of what the observations say. And then the last thing I was thinking in your comments was those ones that come back from the east, I wonder if there was a way to get, they're really rare, but I wonder if it's that the lake breeze from Lake Michigan on the perfect kind of day has made its way so far west that it actually can push disturbances a little bit back to the east upon them encountering it. I don't know if that's true or not. I think sometimes a lake breeze can extend that far, but the conditions are very precise for that to happen. But that would account for the rarity.
The so-called Blue Mounds effect appears to be the theme for the day. Dan emailed with a question about weather systems splitting or going around certain areas. He's heard stories of storms dissipating when they reach the Anago area because of the silt loam soil. Could soil in certain areas affect the weather? I've also seen stories in the last couple of weeks about corn sweat and what corn sweat could do to weather.
So corn sweat, I could see it for sure because there's so much of it. But again, it's going to be in a larger scale because what the corn sweat is doing is putting water vapor into the atmosphere that then the storms can tap into and precipitate out. The soil, again, I think would be, where in my mind, where soil really has an impact is when there's no vegetation on it. Because then you're going to get the big temperature differences, the really hot land and the cooler atmosphere that would support convection. But if it's got vegetation on it, I'm not sure that it would have that much of an effect.
No, and if it's saturated, let's say it had a rain the day before, it might act like a cornfield in mid-July because then it's got a lot of evaporation coming out of it. It's kind of what you were thinking about on the other side of the coin. So that's, without knowing more details, that's hard to know. But these things, it's interesting that summertime weather systems really can respond to some of these local vegetation / water on the ground / dry ground aspects.
And this is why, personally, in the summertime, if I want to go outside and work in the garden or do something, and I look up and it's cloudy or I hear thunder, I'm on that radar app. And looking.
Absolutely.
Where is it? What's coming? And is it dissipating or intensifying? Because a lot of times it'll be raining all around, but not at our house. And when you look at the radar, you can say, it's just the process that entire storm has been developing.
And it's amazing now how prevalent a time series of fundamental observations is to people's daily lives. And that's what it is. When you watch your radar animation, it's a time
to
series
the phone
of
to
fundamental
find out,
obs.
to get the surrounding area, find out where you're in the thick of it or where the thick of it is. It's just to think of the anecdotal, what I see in the skies and how does this play into the, is the soil shifting the weather, is the lake shifting it? And then to get down to such a fine point in our forecasting. When did we get so good at weather forecasting that you've got a 7-day forecast that you could believe or rely on?
That's a good question. That's been a slow, evolving, silent revolution.
Oh, my gosh.
And I would say that I always preface it this way. If you can paint the complexion of the day 7 days out fairly accurately most of the time, that's a good forecast. You're not going to get a point-specific accurate forecast. It's going to rain today at 2 o'clock or next Sunday, 2 o'clock. So if you have that expectation, it's not reasonable. But that's probably evolved since I've been here. I don't think when I came here in 1994, we could actually say that. We were thinking about 3 and 5 days as sort of the frontier. Now 7 to 10 is the frontier. So that's been within the last 3 decades.
I remember a local weatherman in Madison who would have plus or minus 4 degrees for his forecast for the next day. And now that was like a contest. If they got it wrong, they'd give out umbrellas. But
That's right.
now you just expect it every day within 4 degrees.
Yeah,
Right.
it's just remarkable.
Oh.
And to think about how we easily take it, I'm not blaming anybody, but we take
Don't even
that
think
for
about
granted.
it.
And
It's too easy.
all of our grandparents and many people's parents do not have that aspect of their lives at all.
And the bigger picture, what that does mean for transportation, for agriculture, for business, it's mind-boggling.
It is. It is.
Yeah, I do this talk, John knows, about the Edmund Fitzgerald, which went down in 1975. And the comparisons I make is that in 1940, we had the big Armistice Day storm, and that killed over 60 people because they had no idea it was coming. In 75, they knew it was coming, but the forecast wasn't as accurate as it needed to be when they made their adjustment to their ship, and then all 29 people died on it. In 1998, almost exactly the same storm as 1975 and 1940. And the National Weather Service forecasted it right. Nobody died.
Yeah, it's right on the money.
It's right
Days
on the
in
money.
advance.
So not just transportation and agriculture, but lives, life and death.
Yeah.
Something to think about.
It is.
Let's go to Randy and Ripon next. Randy, good afternoon. You're on the air with the Weather Guys.
Hi. Back when we had 9/11, public radio had a guest on talking about, because they had grounded all commercial flights, and they had a guest on talking about the measurement of sunlight hitting the planet and how there was a spike after that, whatever it was, a week or whatever, several days, in the amount of sunlight hitting. And I've often wondered, because here in Ripon, there's a flight path from Milwaukee to Minneapolis, and I always see the contrails leaving shadows across the ground. And I'm just wondering, is that still a factor? Because this guest had said they thought the global temperatures would be about 2 degrees warmer if it wasn't for that shape.
I seem to remember something about the jet airstreams, the contrails clearing the skies after September 11th, 2001.
Yeah, I remember that too. And I don't remember, I'll have to go back and look this up, but if I remember, was it associated with the cloudiness going down? Because, with no airplanes allowed to fly over the U.S., you're not going to get those contrails, and that increases cloudiness. Or if it was surface temperatures, because when you have contrails up there, they can reflect solar energy, but they also emit infrared radiation down to the surface. And so thin cirrus clouds tend to warm the planet, not cool it, as opposed to thick stratocumulus clouds, low-level clouds, which will cool the planet, not warm it. So I remember there was that study. I just don't remember what the results
Me too.
were.
And I'm equally vague on that, on some of the details. One of them was, I thought it was somebody in the UW system, UW Park Falls or UW River Falls.
His name, all of a sudden I'm going to yell at his name.
It's right there on the tip of your tongue.
And I thought that the result was that overnight lows were a little bit lower, but the daytime highs, there was no significant change over that short period of time.
Yeah, I think that's what. Yeah, well, he was at Whitewater.
Whitewater, that's it. Yeah.
Great question, Randy, and thank you for that. Speaking of overnight lows, Libby emailed. She has an above-ground pool heated by a solar blanket. She says that it seems as early as August, the water doesn't get that warm, and she thinks it cools off so much more at night. Is it traditionally much cooler at night in August than June or July, or is she wrong about her solar blanket on her pool?
She's not wrong.
Really?
When you get to August 21st, you have the same length of day as you had on April 21st. So you have longer night, and that makes a difference. Absolutely right. And you don't see it so much in early July. I bet you'd see it right now in late July, but not so much in early July. You're right around the solstice. But by the time you get to August, no doubt. And in addition, probably slightly drier air so that the radiation is able to get out of the atmosphere a little bit better than it was in July or late June. So there's a couple of things working against you there.
Wow, interesting. I never would have thought
Yeah.
that.
Oh, well, when you think
That's a
about
heck of
it,
an observation
Yeah.
she's making, too.
Yeah. Right on that. Yeah.
Libby, way to go, and I really appreciate the email and way to think it through with your pool. I appreciate that. We had 3 tornadoes reported touching down, according to the National Weather Service in Green Bay last Wednesday. The Wausau ABC affiliate weather says that they have, Wisconsin has had 33 tornadoes so far in 2025. They say that it's normal to see about 23 for the entire year. And yet it doesn't seem like it's been that unstable for tornadoes this season. I'm wondering what you guys have seen in terms of severe weather.
So, yeah, I was surprised that we have 33 already tornadoes. So I'm wondering, well, we did have one in February, too, for the first time. So that might be part of it as well. But, yeah, I think I would be interesting to know what the distribution is. Are the F-Zeros the really weakest ones? I don't think we've had any F-5s or F-4s.
They tend to make pretty widespread news when they're that kind of devastation. Yeah, but I think it's, and the other thing for us down the southern part of the state is that there've been more in the northern part of the state. I would guess splitting the state in those halves, I would guess 2/3 or more of them have been in the northern half of the state.
Okay.
Not so much here.
Was the February tornado this year or last year?
Might have been last year.
Was it last year?
I can't remember if it was last year or this year.
But is tornado season not what it used to be?
I don't think I'd be ready to draw that conclusion.
Okay.
I think no. I don't think that's the case at all. It's shifted a little bit. Tornado Alley shifted a little bit to the east. Recent research out of Northern Illinois University in Oklahoma has kind of said that. But the number of storms, I don't think has changed substantially. The number of most intense ones hasn't changed substantially. So I don't think so. Nationwide, anyway. Statewide might be different.
What have we seen in this year's hurricane season? I thought we were expecting I would just ask you your expectations of this hurricane season and what we've seen so far.
I think we had 2 named storms, I think. We got up to the letter B.
Right.
Maybe. And they haven't been particularly impactful. That doesn't mean they weren't strong. I don't know.
Right. Yeah.
They could stay off.
Land.
Yeah, if they don't hit land, we don't have such a focus on them. But honestly, by the end of July, that's not usually a time where you've really seen any substantial hurricane activity in the Atlantic Basin. It starts to rev up now, right at the end of the month, early August, mid-August particularly. Mid-August to the end of September is the time to be really concerned. So far it's behaved like a normal season, I would say.
That's John Martin, professor and former chair of the Atmospheric and Oceanic Sciences at UW-Madison. Also joining us, the other half of the weather guy, Steve Ackerman, emeritus professor at UW-Madison's Department of Atmospheric and Oceanic Sciences. Want to invite you to our weather conversation at 1-800-642-1234. That's 800-642-1234, or email us, talk@WPR.org. I'm Lee Rayburn in for Larry today, and this is The Larry Miller Show. Coming up tomorrow on The Larry Miller Show, the new book, Piracy on the Great Lakes. We'll learn about the buccaneers of our inland seas, then talk about the planned city of Greendale, and we'll be joined by the editor of Lake Superior Magazine, all tomorrow from 11 to 1 on The Larry Miller Show here on WPR News. But right now, we have the weather guys joining us. Steve Ackerman and John Martin are here to answer your questions for the remainder of the hour, but you're going to want to get them in quick, so give us a call, 800-642-1234. That's 800-642-1234, or email talk@WPR.org. Got another email here, and this seems to be the theme of our day, watching weather systems divide and what may be causing that. Mark emailed to share another geographic feature affecting the weather, the Niagara Escarpment, which he says causes westward heading weather systems to split at Lake Poygan, causing 2 systems that go north and south, which misses the eastern shore of Lake Winneconne. You know anything about this, Steve?
No, I don't. But now we're talking about geographic features that are bigger.
The
Niagara
the escarpment's huge
big.
and goes on forever.
Right.
Yeah.
And so when you start getting large things, like certainly the Rocky Mountains impact storms as well.
Yeah.
But again, I think it would take that study to look. And it also would depend on the storms. I can't imagine a big mid-latitude storm in November or December really caring about what terrain is.
Rides roughshod over all of it. But in the summertime, maybe the direction of the flow at certain levels can really have some impact on generation or sustenance of those storms.
Or
But
kick it off.
Kick it off. Initiation even. Yeah.
Certainly feels like something that would deserve to be explored a little more, considering how many anecdotal stories we've heard about it and how many different places claim to actually impact the weather, even though, as you both point out, the weather system's usually going to be the stronger of the two.
Yeah.
But it's great that people are paying attention.
I know.
think,
Yeah,
right?
that's right. That's right.
Everybody loves the weather.
It's hard not to.
Well, the funny thing to me is it's Wisconsin, and it's the one thing we like talking about. We love talking about the weather. To me, it's the kindness, because it's a common ground we all share.
Yeah.
So if we want to find common ground among even strangers on the streets in Wisconsin, we can always fall back on the weather, because it's a thing that we share together, and it's a nice starting point.
Yeah, and it varies throughout the year.
Yeah,
too.
it does.
And it's interesting.
Yeah, there's nothing more interesting.
That's according to John Martin now.
The weather guy.
We learned last week that the National Oceanic and Atmospheric Administration's weather radios weren't working in parts of western Wisconsin. Last Wednesday, service from the weather transmitter located in Wheeler was restored. But how serious is a problem when the weather radios start malfunctioning?
I think in some rural areas, it's really important because, anyway, they rely on that to tell is severe weather coming. Where the warnings are going to be issued, where the watches are going to be issued, they're coming across on that weather radio. So if there's a large geographic or even a small geographic, anybody who depends on that to know if severe weather is coming, it's not a good thing.
No, it's not. I mean, this wasn't the case in the Texas flood, the tragedy that happened a couple of weeks ago. There were warnings going out on the NOAA radios. They just weren't widespread in use,
right?
And so people weren't receiving that news that was being offered free from the government. So they're a big deal. You got to get that fixed.
Well, and I interviewed the director of the Outagamie County Emergency Management, and they give those weather radios out as part of their weather alert system.
Yeah.
And it wasn't out that long, right? I mean, it wasn't like they were
a few
out
days,
for,
I think.
Yeah.
Would you recommend getting a weather radio? If you get the alerts on your phone, is a weather radio...
The weather radio will wake you up in the middle of the night. Your phone might not do that. So, I mean, if I'm really... Let's say I have some interest or some particular fear of such storms, I would definitely get one.
Yeah.
Yep.
Mike in Dunn County, we'll go to you next. Good afternoon.
Hi. I was... recently at a baseball game for one of my grandkids, and there was a storm approaching. It was hot and humid. And I thought, I think they should get the kids off the field. And they said, oh, no, we don't have to, because if the lightning's not coming straight down, that would be worse, but if it goes across the sky, we should be safe. So I just want to know what's your attitude on that, and I'll take an answer up there.
Mike, I'm telling you, it does not look good in the studio right now. The expressions of our weather guys.
Yeah. And if you hear lightning, you should not be on a baseball field.
Yeah, my kids played in UW-Madison for years here in town. Great league. And I coached for a number of years. I was amazed at how good everybody got at reading the radar. And the other thing was really important. As soon as thunder was heard, umpires take everybody off the field. 30 minutes transpire. If we don't hear any more thunder in that 30 minutes, we can take the field again. That's the only threshold. So you got to get off the field when you hear thunder.
So
no questions asked.
Lightning sideways is just as dangerous or deadly than lightning up and down.
Lightning sideways may turn your day sideways. So you got to get off the field. Yep.
And is that just how the electron charge interacts with the spark? What decides where the lightning goes?
It's pretty much up to the lightning into the atmosphere, so they'll set up a channel, and that's what the lightning will follow. When it's hitting land, the land surface, whether it's a tree or a building, is helping to set up what that channel is.
Okay.
But you can get cloud-to-cloud lightning as well, and that's when you're getting that horizontal one. so it's traveling from one part of a cloud to another.
But a storm doesn't have a preference whether it connects to the cloud or the ground. It's just looking for that connection.
That channel. It's got a lot of charge, and it's trying to get rid of it.
And there's no observation you can make that can lead you to conclude that you've correctly assessed that it's not going to drop it to the ground. You can't do that.
That's not the lightning that'll get us. Any lightning can get you. You two recently wrote a column about how rainfall intensity is changing. Is that anecdotal? Is that real?
No, that was real. That was a question that somebody, we do on a column for the paper as well, and somebody wrote and asked about that. It was very interesting, I thought, because I didn't know. But is it, rainfall's going up, but is it going up just in the mean? Or are we getting more small events? Or are we getting more larger events? And it turns out we're getting less events that have more rain in them, which is really interesting because it's telling you that the storm dynamics are changing. It's not just about the water vapor in the atmosphere, which is what I was typically thinking of.
Yeah, can I just tell a little short story about this? Steve, we received these notes from people together. You got particularly interested in this, and at first, he was thinking just what you said. Right. And then he said, let me look at this again. So this percolated for a couple of weeks before it showed up in the article you wrote, and it was really excellent work. I remember I could tell you were on the trail of this. You were really into that.
It's like here, we get a lot of interesting people making their own observations and then wondering. So I'm going to start looking at the radar and see if it's going around the lake.
Yeah, right.
So the rainfall then, it is happening, it is more intense, but it's happening in shorter bursts?
I wouldn't say shorter, but it's coming in heavier events. So when it rains, so what they did was they looked at 2 20-year periods, and the last one, I think, ended in 2014 or something like that, in the mid-20s, because that's when the data was good. And then they broke it up into light rain, moderate rain, and heavy rain, because that's how we typically categorize it. And what they found was there were less cases of light rain and more cases of heavy rain.
Does this change what we would do in terms of flood mitigation, do you think? Or how we would plan for 100-year floods?
I would think so, because if you have light rain, heavy rain is, of course, the urban flooding in general.
Right, city engineers would pay attention to that in a lot of places. If you're getting more frequent heavy events, the kind that already your system struggles with, you're going to have to make some adjustments to your system if they're going to become more numerous. Yeah.
I want to try a weather term on you guys, see if you can spell it out for me. Mesoscale convective complex. What's a mesoscale convective complex?
I'll take the last C. It's a complex of storms.
They're smaller scale, so they're the scale of a state in the United States.
Okay.
Smaller scale than what we get for wintertime cyclones, the kind that can deliver precipitation over 10 states at once. But they're a summertime phenomena usually, and they're a collection of thunderstorms that in their organization, they create a circulation amongst themselves, not just individually. And so
a storm of storms?
Yeah, and they become a long-lived entity. They can sometimes live for 2 straight days, and they don't move very much. So when you get an MCC, a mesoscale convective complex, over you, and it's a non-translational one, which is some large fraction of the total of such events, it'll stay over the state of Missouri for 36 hours, and places will just get inundated for that period of time. So they're really interesting phenomena, and they're a summertime phenomena in the central plains of the United States.
How common are they?
I'd say you get through a couple every single summer.
Okay.
I would say.
But I don't necessarily hear it or see it on my app as a mesoscale convective complex.
Yeah, probably not. They're just going to say, you might notice that you get 3 straight days of moderate to heavy rain or something like that. And you say, what's going on with that? Well, you're underneath one of these probably.
Let's see if we can fit one more question in quick here. Martin from Middleton, good afternoon.
Oh, hi. Yeah, thanks for getting me in. Is there such a thing as a micro tornado? Twice now, in the Madison area, I've seen these little corkscrew things. It looks like a pig's tail hanging down from a cloud high up in the sky. It moves a little bit, and I've watched them for a couple of minutes, and then they disappear.
I don't doubt it. I think one of the elements in the larger tornadic funnels that develop is something called suction vortices. They're much smaller scale, and something goes on in those storms that organizes a collection of those suction vortices and creates one larger funnel. So what you're seeing, I think, is an aborted tornado formation. You've got a couple of little suction vortices that are coming out of the clouds, but there's not enough, whatever the extra ingredient is. I'm not an expert on this. Whatever that extra ingredient is to organize or maybe amplify those first few vortices.
So you wouldn't call it a micro tornado. You'd call it a start of a tornado.
Yeah, they have a formal name called suction vortices, and they are elements of the origin of the bigger funnels. Yeah.
And it can only be a tornado if it touches ground.
Oh, yeah, there you go. That's the other thing.
Technically, it's not a tornado.
So what is it before it touches ground, or if it doesn't?
It could be a vortex or a funnel cloud. So
Okay.
sometimes you'll see a funnel hang down from a cloud, and that's, as John's pointing out, it's just the circulation wants to develop a tornado, but it may not get down to the surface and start destruction.
That's an important distinction,
Guys, we are out of time, but I want to thank you for yours and your expertise as always. Really enjoy the perspective, and I want to thank all the callers from calling in because they seem to find a central theme that we grab onto, and today was weather systems splitting in half.
Yeah, I'm going to be watching that radar.
Who knows what reason? And maybe there is research to be done to learn a thing or two in the days, years ahead. Thank you both for joining us today. Very much appreciate it.
Thank you, Joel.
Steve Ackerman is a former Vice Chancellor for Research and Graduate Education at UW-Madison and Emeritus Professor in the Department of Atmospheric and Oceanic Sciences. John Martin is a Professor and former Chair of Atmospheric and Oceanic Sciences at UW-Madison. Thanks to them and thanks to you for joining us today as well. It's a product of our team, the Larry Mealer team here, Clara Neipert, Joel Patnod, Jeff Robbins, our executive producer, Jill Nadeau. Thanks to them all, especially our own Larry Mealer, who will be returning later this week. I'm Lee Rayburn in for Larry today, and you're listening to WPR News.